Hello and welcome to our last podcast on Unit 4 covering Section 11.5.
Which is the Hydrates,
I'm Mr. Sakaguchi,
and I am Mr. Lin.
so let's get started. So what is a hydrate first of all? Basically, it's a special kind of ionic type of compound where water kind of adheres to the ions as a solid forms.
And as a result, the water becomes part of the crystalline structure, and it changes around with some of its physical properties as a result.
Yeah, and basically we end up with compounds with specific number of water molecules around the atoms. And so what you see here on the right is an example of one kind of hydrate. And there are other ones that we'll talk about and their uses and their importance.
Pretty.
So how do you name a hydrate? Hydrates have their own naming system to be aware of. Basically, we need to indicate how many water molecules are associated with each formula unit. Usually, when we're writing a formula, we usually have a dot and then a certain number of water molecules. This is always a whole number. It could be 1, it could be bigger than that. And basically, we use our molecular prefixes, and then we use hydrate for water. So for this one, this would be sodium carbonate decahydrate. Deca for 10 and hydrate for water.
And whenever we're describing hydrates, you have to understand that the mass of water has to be part of the molar mass because it's very specific. Different compounds will have different amounts of water molecules attached to them.
Hydrates have many uses. The anhydrous forms absorb water into their crystal structure. These are also used as desiccants.
What that means is it's a substance that just absorbs water. Sometimes you might open up some sort of food item or electronics, and you'll see these little white packets inside. That's an anhydrous hydrate. It's to absorb moisture so that your electronic stuff doesn't get rust on the inside, and it's also sometimes used with like chips or something to keep the chips dry and crispy.
And often you'll see them inside leather shoes and leather goods as well. Some will store solar energy. As temperature increases, crystals dissolve, and the water will store the energy. And as the crystal cools off, the solar energy is released. Analyzing hydrate. If we want to know how many waters are associated with a particular hydrate, we first have to remove all the water. Usually we do this by heating, which causes the water to evaporate out.
And as you can see in the picture to the right, there are some hydrates that change colors as the water leaves because the crystals rearrange their structure and as a result refract light differently, and so we perceive that as a different color.
And so if you see anhydrous used to describe something, that's basically a hydrate that has had all of its water molecules removed.
Dried out.
So let's say we wanted to know the formula of a hydrate. So basically, again, what we're trying to do is we're trying to figure out how many water molecules there are per formula unit of the ionic compound. So let's say we have 5 grams of a hydrate of BaCl2. So the actual formula for that hydrate would be BaCl2 times some unknown number of molecules of water, which we'll call X. Now, what we're essentially doing in this problem is we're going to find X. What we can do here to help us figure that out is we can remove the water by heating it. So the anhydrous BaCl2, let's say, has a mass of 4.26.
And what we're going to do is we're going to undergo a calculation process similar to how we did the empirical formulas.
So the first thing we need to do is we need to figure how much water is present in the hydrate. So the way we do that is we take the difference between the hydrate and the anhydrous salt, which leads us to 0.74 grams of water. So what we're going to do is now we have our grams of BaCl2. We're going to convert this to moles by finding the molar mass of BaCl2. And when we do this, we get 0.0205 moles of BaCl2. So now we're also going to find moles of water. We multiply by 1 mole over the molar mass of water, giving us 0.041 moles of water.
That's how much water was removed when we dried it out.
So just like with the empirical formula, we're finding moles because we're going to do a mole ratio. But instead of the mole ratio being between atoms. It's going to be between the salt and the water. Just like with the empirical formula, we're going to divide by the value that is the least out of these two, which is the 0.0205. And when we do this, we get a 2-to-1 ratio. So basically, for every 1 mole of barium chloride, we have 2 moles of water. So our hydrate, our X in our hydrate is going to be 2.
And we would call this barium chloride dihydrate.
And that is it.
Yep.